Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, and I'm here with another episode of Ask Dave. Today's question is kind of interesting. It's from Lester Paul. Oh, he's still working on his license. Now, he's kind of curious about an interesting little feature of the way HF propagates by bouncing off the ionosphere. If you send up a plane wave, meaning it's flat, all in one plane, P-L-A-N-E, either vertical or horizontal, or it doesn't matter, when it hits the ionosphere, it will be broken into two waves, the O wave, or ordinary wave, and the X wave, or extraordinary wave. Now, these are circularly polarized, one going one direction, the other going the other. The ordinary wave seems to have most of the power, and the extraordinary wave has a significant amount of power, just not all of it. What happens is that as these waves propagate through the ionosphere, they go in slightly different directions. Now, I know that's quite a leap from our standard understanding of the ionosphere, something that refracts waves. Yes, it does, but it also splits them into their two circularly polarized counterparts. Now, since it goes different ways, you might be receiving the ordinary wave. That would be the ordinary way of doing things. You know what ordinary means, kind of drab and not much to look at. But the extraordinary, wow. If you are receiving the extraordinary wave, you're getting a wave from a different direction, and you might be able to do some pretty good things with that. What I want to show you, and what I want to show Lester here, is about building an antenna that can receive either the extraordinary wave or the ordinary wave. In other words, circularly polarized antenna that you can flip the polarization on to see which is strongest for you. Now, I might point out that these point pretty much straight up. If they go off to the side, you get what's called oblique polarization. Okay. Now, let's just take a look at this. And I'm going to put a pole in the middle because it's convenient to have that. And you'll have a pole over here and a pole over here and one over here and one over here. These are, if you look at it from the top, they're like this. Okay. Now I'm going to draw a green dipole, like 20 meters. This is easy for 20 meters. And you're going to put a dipole across here, or in other words, here, like this. This is the center where the feed will go. And then we're going to draw another dipole like this. In other words, like this, the same spot. Now you don't connect them together. What you do is let's say this is the input to the red dipole, okay? This is the input to the green dipole. You're going to take, well, I mean, you can put balance in here if you want, but I'm going to do it the quick and dirty way. Take this, okay, and this, and put the center conductor here, the shield here, whatever, and come around like this, and then connect into there, okay? Here's a lambda over 4. So it's a 90-degree phase shift. Now this is 90-degree electrical degrees, okay? So if you're using a cable that has a velocity factor of 0.88, you take the quarter wavelength and multiply it by 0.88 to get this 90-degree phase relationship. Now, if you feed this antenna here, that means that the other antenna will lag behind 90 degrees. Okay? And we're going to feed that, and this one's going to lag behind 90 degrees, and you end up getting a circularly polarized wave. If, however, you feed them opposite each other, which means here and here, you get a polarized wave going the other way. Okay, now this will probably work up to about 45 degrees to the horizontal. After that, it gets a little weird, because you start get obliquely polarized waves. But this is a very interesting way to play with it. You can put a little relay up here that'll do that. What this does is it switches it around so it hits, here it hits the green element first, and then comes around and hits the red element 90 degrees later. Or if you feed the red element first, it'll flip around and hit this one the other way. So you can get a circularly polarized wave either way. Now note, you don't get both at the same time. Okay, so this is something that is, you can play with this to get circularly polarized waves. Now this is 20 meters, so these need to be 33 feet tall. Try it on 10 meters, you can cut that in half, 17 feet tall for each of these, and just play with it, see what happens with it. You'll find that switching, you need a relay to do this. Switching from one to the other will cause you to receive different signal strengths. One thing to notice is that the ionosphere is fickle, it's constantly changing and moving around, and you might find that whereas the O wave was giving you the best signal, suddenly the X wave is giving you the best signal. If you have a receiver that can receive on two receive antennas at the same time, you can start playing games with polarization diversity, because it might go one way 1 minute and 1 minute the next, and you end up getting overall a steadier signal. So this is one of those citizen science experiments that you can play with and see what it'll do for you. It might do some very interesting things for you. So there you have it, a way to play with circular polarization on HF. And until we next meet, 73.